I would like to get started because I have a really long-winded introduction about Gary. I don't know where to start with Gary because he's a Renaissance geophysicist or geoscientist. He's done so many things that I just have a lot of stories about Jerry, but I'll try not to be too lengthy. I met him through Geos 220, which is the geophysics undergraduate class here at Boise State University. I think it is a great drug to geophysics. Although not many people end up going on and taking more drugs. So, they usually like decide I'm done with that. But no, Jerry, for some reason, liked geophysics a whole heck of a lot. And so he ended up going to the emphasis program and started to work in my lab, which, as many of you know, constructs infrasound sensors. And immediately, Jerry was a huge asset to that lab because his problem solving, his engineering was just off the charts. Partly maybe due to the fact that he had operated a business for a few years before coming back to school at Boise State University. Is to blow up rodents.
No, yeah, go for it. Yeah.
So,
This is all true.
Yeah. And that was not only did he run a business, but he had to engineer how to kill these critters, tunnels with diesel gas fumes and explosions without hurting himself.
Not always successful. Not always successfully.
Yeah, and so he was still doing this job as he started to become a full-time student. Long story short, he's finished his undergraduate degree, had the opportunity to travel to Chile with some of us and engage in volcano geophysics using infrasound sensors to listen to volcanoes and presented those results at a conference and did an undergraduate thesis related to volcano infrasound. And then decided to stick around for a master's degree. So that's what we're going to talk about today, is Jerry's master's degree. But when I say he's accomplished or he's got a wide, it's an understatement to say that he's got a lot of diverse interests. The infrasound he became an expert on. He also worked for HP and built sensors to measure snow properties, snow growth. And then he got really into drones. And so he started flying drones to make maps. That's what we see today. And not only did he, quickly exhaust the abilities and the knowledge of his advisor, but he went way beyond to make maps of dynamic topography in Guatemala, where we also had an infrasound experiment. And this turned into an awesome thesis project. So I'm going to give him a lot of credit for going in so many different directions, but getting it all done as well. All in the space of just a couple of years of a master's degree. With a little bit of entry as an undergraduate. And then the other thing I need to mention before I move on is like Jerry's contributions outside of academics are appreciated. He has been a vital force in the department in a number of ways, and in Guatemala. He's actually done a lot of the stuff that you'll see today. He's taken to colleagues in Guatemala and educated them on these processes. So I guess I would like to say that the outreach component of the work is appreciated as well. So yeah, he's done a lot. Hope to keep around a little longer. We'll see how today goes first.
All right. No pressure, right? Okay, so thank you, Jeff, for that very thorough introduction. Today, I'll be talking about UAS-based quantification of dynamic Lahar channel morphology at Volcán de Fuego in Guatemala. So I'll start off with a shameless plug. So this is my published work, UAV-based quantification of dynamic Lahar channel morphology at Volcán de Fuego in Guatemala. This was published in MDPI Remote Sensing, which is an open access journal, which was really important to me to make sure that science stays available to the public. So my motivation for this work, apart from already being in Guatemala and having a drone and needing something to do for my master's work, is the fact that Lahars are extremely dangerous and are responsible for about 26% of the deaths associated with volcanic activity since like 1500 AD. and they're extremely destructive. They're a natural force to be reckoned with. The deadliest Lahar was in Armero, Colombia in 1985, and that claimed 28,000 lives. That was a primary Lahar, so that required eruptive activity to trigger. But Lahars aren't limited to just eruptive activity to be triggered. Secondary Lahars can be triggered by just the local weather on the side of a volcano. For example, in October of '98, Casita volcano in Nicaragua was hit by a hurricane, and that hurricane caused an avalanche and Lahars, which claimed an estimated 1,600 people. Notably, that volcano had not been recorded to erupt in human history. So it was a very, very old dormant volcano, and it still claimed 1,600 people. So I'll go over some key points to keep in mind as I go through this talk. The largest secondary Lahar volume at Fuego during the rainy season of 2021 were a net 493 cubic meters per day loss in the upper reaches and 438 cubic meters per day gain in the lower reaches. So we've got a shift of volume from up to down. The morphological activity factor is a novel metric, which shows the overall changes in channel when both erosion and deposition are taking place. And a natural channel constriction and immediate widening of Las Lajas controls the behavior and stability of the stream below that point. Las Lajas is the stream channel where all of my research took place. And finally, the quantification of the sinuosity index over time is a useful geomorphological parameter because it shows that the Lahars are actively and drastically changing the flow path. So I'll take you to where we're going, where all of our work happened. Down here in Volcán de Fuego in Guatemala. This is Fuego. It's a very, very active volcano. And down this channel, Las Lajas, is where our work was done. So I'll say a little bit about Fuego. So Fuego's been in an active period since 1999. It has regular eruptions, 4 to 15 small Strombolian-style eruptions per hour, consisting of ash, blocks, and bombs. There was a temporary decrease in activity after the June 3rd, 2018 VEI-3 eruption. VEI stands for Volcanic Explosivity Index. This is a logarithmic scale. For example, a VEI-2 has greater than 1 million cubic meters of material erupted and a plume 1 to 5 kilometers high. And then a VEI-4 has 100 million cubic meters of material and a plume 10 to 15 kilometers high. So the June 3rd, 2018 eruption, 12 kilometers of the Las Lajas drainage was filled with 15 million cubic meters of material, 400 to 1,000 people killed in the town of San Miguel Los Lotes when the pyroclastic current jumped a bank and carried on outside of the channel. It was powerful enough to jump and hit that village. 1.6 million people were directly impacted by the ashfall. There was intense structural damage to a major bridge that crossed that channel, some 12 kilometers away, 10 kilometers away. And there was also the destruction of the La Reunion golf resort. The back nine was completely destroyed. So Lahars have a very specific anatomy. They consist of volcanic material and debris because they happen on the side of a volcano. They exhibit some pulsing behavior. They have a watery front, a bouldery snout, and a watery tail, as I've circled on the figure there. They are capable of extreme erosion and deposition in a short span. So I'll show you a video of a Lahar or a set of pulses. You can see here that that bank across the way is 15 meters tall. And this is all cutting through that pyroclastic material from the 2018 set of pyroclastic currents. You see it pulsing. See the major erosion happening on the opposite bank. I should mention that this is a medium-sized Lahar. This is part of the other study that was going on during our time in Guatemala with infrasound and cameras set up along the flow path. So UAS-based change detection through differencing of digital elevation models is well-established science. It's been used at Stromboli volcano in Italy for change detection before and after eruptions. It's been used in post-fire erosion studies by some of the alumni in our own backyard. And to study river channel erosions in Antalya, Turkey. This technique is established and useful for detecting change and making accurate volume estimations. So I'll go back over our study site here. So this up in the top left corner is Volcán de Fuego. The red triangle is the rain gauge that I got some data from my colleague at Michigan Tech, Gustavo. And then at the bottom here, you see 4 survey zones. So all of these survey zones were pre-programmed flights through DroneLink software. And you can see on the left, that table, there was 4 sets of flights. So each of those flights has a date on it. For instance, 210607 was June 7th. And below that is the number of photos taken for each flight. The red squares in the table are data that I don't have. I will mention that Armando Pineda was gracious enough to collect 2 sets of those surveys. So the drone that I used was the DJI Mavic Air 2. We named it Air 2 Brute. So on the right is an example of the pre-programmed flight path and DroneLink. We programmed this after we got down there. So none of this was planned beforehand. It was all a little bit off the cuff. So we got DroneLink, and then I learned how to use it, and then I programmed this flight. Unfortunately, DroneLink doesn't have the capability to do terrain tracking. And on the side of a mountain, that proposes certain challenges because my altitude was completely constant over the entire flight path. So I had 100 meters of altitude at the top and the bottom of this flight plan, which means at the top I had 20 meters and at the bottom it was way over 100. So that limited my ability to make long flight paths, which is why there's 4 survey zones instead of 2 survey zones. But the DJI Mavic Air 2 has a 1/2-inch RGB sensor. It's pretty lightweight, which makes it very easy to pack up and down a volcano with a flight time around 30 minutes. So this is a pretty busy slide. The Lahar occurrences and rainfall events during the 2021 season. You can see on the left-hand side, we have rainfall in millimeters. On the right-hand side, we have relative Lahar intensity, 1 through 3. And then across the bottom, we've got the dates. We have time series. Across the top, we've got lines indicating when the surveys happen, survey 1, 2, 3, and 4. You can see the black stars are the Insivume reported Lahar events. the Lahar intensity ranging from 0 to 3, 3 being the highest intensity, 0 being not a Lahar. The red dots are the camera recorded Lahars. This was done with the other study that we had going on with the infrasound and cameras. Ashley Bosa was kind enough to give me her catalog as well as Insavume. Notably, Insavume uses seismic methods to catalog and rate all of their Lahar events. They use seismic instead of any kind of video or anything like that. So it's notable that in each time span, the number of Lahars stays pretty much the same, with an average of 6.5 Lahars per time step. That wasn't on purpose, it's just a happy accident. We were able to discount any fluctuation that way. So since all of our Lahars are the same throughout, any erosion that happened, we can count that as a constant. We don't need to count that in any other way. So I'm going to go through the methods that I took to get our final data. So in Agisoft, it calls for 10 to 12 synthetic, or well, ground control points. We weren't able to actually get ground control points in this study because, as we mentioned before, we didn't really have a plan going in. So I used markers on the corners of very distinctive looking rocks and the intersections of sidewalks and so on and so forth to co-register, not geo-register, all of my digital elevation models together. So you can see here, I've delineated D, E, F, and G sections. Those will come in later. Those are the 500-meter delineations. But I just wanted to point out that E and F are the ones that we're going to be looking at the most. So this is the Agisoft workflow. It's a lot to take in, so I'm not going to ask you to read basically any of it. But I've marked out the main points here. So number one, we read in the data, pretty standard. 2, we optimize the camera positions and eliminate any errant sparse cloud tie points. Number 3, we build the dense cloud and eliminate yet more errant points. And then 4, we build the digital elevation model and orthomosaic, and then we export our data products into some usable form. So there was a big problem with all of the vegetation when doing data differencing. So vegetation has this bad habit of growing over time, especially in Central America. So that added volume really threw off all of my numbers. So I had to go through and remove it. I used QGIS to process that out. I started with creating regions of interest, delineating training for plant versus rock. I only used 2, I should have used more. It ended up working out. So you can see in panel 1, that's the raw classification. You can almost see that there are very, very small red speckles in the shadows of rocks. So I didn't want to have all of those holes. So I used the sieving tool and the semi-automatic classification plugin to take out anything below 4 pixels grouped together. Once that was done, I noticed that there was quite a bit of green still poking through on the edges, which is the part where it's really, really going to throw everything off. So I ended up using a dilation tool in that same plugin to expand all of my regions by 4 pixels. So buffered everything out by 4 pixels. And that was able to account for all of the green space. And this is what it turned out. This is how it turned out. So this is all 4 of the survey zones stitched together and then split into 500-meter sections to do all of my statistics on. So in the end, I did end up trimming most of this digital elevation model away, but it's not very interesting to look at. So I'll leave you with this. So after that, I did some data differencing. I subtracted digital elevation models from each other. You can see here the delta VT21, that is the change in volume from time 1 to time 2. And I did that for all 3 of my time steps. So you can see here, I'm pointing out the transition from erosion to deposition in delta 4-3. So the time step between the 3rd and 4th digital elevation models. I'll also note that in the center where that transition happens, it shows in the net volume that there are very, very low numbers in there. So where it's transitioning, even though you can see on the right, there's a mixture of warm colors and cool colors indicating erosion and deposition all in the same part of the channel. So there's erosion and deposition happening simultaneously, which is hidden in this graph. So I split it up. So deposition and erosion, balanced deposition and erosion conceal the overall activity. So we can see that there's actually a lot going on in that transition zone. It's not as cut and dry as we originally thought. So that's when we came up with the morphological activity factor metric of total volume transport or change within the channel. So you can see here, to really demonstrate that D and E, there's a lot going on in that section, then it drops off drastically for F. So the overall erosional regime changes from to depositional in section F. So section F holds the restriction, the channel restriction that I spoke about in the key points. The channel restriction and then immediate widening of the channel, it robs a lot of energy. That's also where the pyroclastic current jumped the bank. So there's less pyroclastic material below that point. So, yeah. So I'll go over the cross sections that I had in the last slide. So this figure is reproduced through MATLAB with a digital elevation model and an orthomosaic draped across the top of it. An orthomosaic, for those who don't know, is the reconstruction of all of the cameras put together and then ortho reference, so it becomes a map view. Everything is looking straight down in any point. So this draped over the digital elevation model creates what they call a 2.5D model. You can see in the plants, they're kind of stretched out. That's where you can tell it's a 2.5D model and not a 3D model because it doesn't have the under curve. So anyway, the erosion at this point, we have 12 meters of lateral erosion. That's nearly 40 feet of lateral movement of the channel from June to October. And then we've got 8 meters of incision after that as well. There's 2.5 meters of deposition on the inside of the channel and the point bar. This is a little bit further downstream, but generally the same thing is happening. It's still cutting down through that pyroclastic material from 2018. Here we have 10 meters of lateral erosion and 5 meters of incision. So this is where everything gets really interesting. So this cross-section is through some very indurated rocks, a very, very hard volcanic material from far before. So this is 12 meters across, give or take. And as you can see, it didn't change hardly at all throughout the rainy season because it's very, very hard rock. It's not going to. And that's essentially stealing a lot of the energy in that choke point, limiting the amount that can get past it. The immediate widening of the channel also does a lot. It acts as like an alluvial fan. It just really robs everything, and it drops all the big pieces that eventually get washed downstream. You can see that the erosional and depositional regimes have basically equaled out. So we don't have any kind of real incision or hard deposition. It's just kind of meandering across this very wide channel, 60 to 80 meters wide. This is also where they built that very, very large bridge that transports thousands of people. This is a really great choice. This is an excellent spot to build that bridge. So we'll move on to sinuosity. So the sinuosity index is the stream flow path length over the straight line path. It's just a measure of the dynamism of the flow path. So to get this, I measured with the lowest neighbor slope calculation in MATLAB. So in a grid of 4 from a seed, whichever one is the smallest, you'll go to that one, and then so on and so forth, smallest, until you run out of stream path. And that's what I did all of these calculations on in these 500-meter sections. So I'll point out that these are the two regimes that we've been talking about this whole time. So A through E are where the sinuosity was pretty great, and then the rest it was not so much. Like there was very little, there was a lot of sinuosity, but not a lot of change in sinuosity. So it was still meandering back and forth because that's what streams do, but it wasn't as dynamic in the lower reaches as it was in the upper. So the reason for that is because it was cutting down through that pyroclastic material from 2018. As it cuts down through, slides will divert the stream path and really keep things mixed up. Like it's very difficult to keep consistent meandering system when there's that much variability in it. So a shift in behavior involves a change in the underlying material, as we've discussed. We can see the change in behavior in section F and the stability of the sinuosity index. So we've got a lot of variability in A through E, as I mentioned, and then from F through I, it cools off, becomes placid and normal. So I'll talk about the relative percent range. The values increase as variability increases. This really shows what I'm talking about. So the max, meaning maximum sinuosity in each section, minimum, also minimum sinuosity in each section, the mean of the sinuosity in each section. So this is by section, how the sinuosity is changing over time. And as you can see, this really proves out what I've been talking about. The sinuosity changes quite a bit in the upper reach, whereas it calms down starting right at F, where that constriction happens. So go back over my key points. The largest secondary Lahar volume changes at Fuego during a typical rainy season were a net 493 cubic meters per day loss in the upper reach and 438 cubic meters per day gain in the lower reach. The morphological activity factor, or MAF, is a novel metric, which shows the overall changes in the channel when both erosion and deposition are taking place. A natural channel constriction and immediate widening of Las Lajas controls the behavior and stability of the stream below that point. And the quantification of the sinuosity index over time is a useful geomorphological parameter because it shows that the Lahars are actively and drastically changing the flow path. So you may be wondering, why does that matter? That's all well and good, Jerry, but who cares? So as Jeff mentioned at the beginning, I have taken what I've learned and put it to use. So streamline workflows for timely hazard assessment and communication with Roberto at Insivume. I'm going to be hosting a UAV workshop for change detection at Cities on Volcanoes in February. And again, collaboration with Insivume for other remote sensing and change detection projects. As you can see on the left, that's the crater of Fuego volcano. I was recently invited down there to do best practices on getting good data in an active volcanic crater. It was not the easiest thing I've ever done in my life, for sure. But we got some really good data. And we were able to take that data and make that stream flow, or yeah, not stream flow, but workflow to get what you see on the right, which is a difference model that we were able to produce in a matter of an hour once we had all of the data processed. So that's from raw pictures all the way to a data product in about an hour. So we were able to do some really cool things, and we were able to get some volume estimations from this workflow. So we've got 388 cubic meters of material moved in the crater of Fuego volcano over a matter of, I think, a few hours for this one. My references. All right, and special thanks to my Guatemalan collaborators, my Michigan Tech collaborators, the National Science Foundation, my Boise State team, and my committee, Jeff, Ellen, and Megan. And another shameless plug. So if you actually really do want to read this paper, if you're interested in any of this, there's a QR code there that you can get it. Thank you. Yes.
It's the MAF, which stands for Morphology.
Morphological activity factor, yeah.
You said that's a novel. Did you create that?
Yes, yeah, that was mine. Yes. Yeah, because I was having trouble with really understanding what was going on, where there was both deposition and erosion. Like reconciling two graphs is a lot more difficult than just the one graph. So I made one graph.
The Strombolian discharge you're talking about, what is that defined as?
So Strombolian eruptions are short bursts. They're ashy and blocky. They don't have any kind of lava, I'm pretty sure. Am I right? Yes, I'm right. I'm getting a thumbs up. So yeah, that's what they are.
Your map of difference in the crater of Fuego,
Mhm.
can you show that again?
Yes.
Curious, you mentioned the volume loss or volume gain during that period of time.
Yes, maybe I can do that again.
Totally off topic, but there was a gap there, so.
Okay.
So we're looking at the right-hand panel there?
Yes, the right-hand panel is
And
the
that's where
difference
you
map.
measured the difference from?
Mhm.
That's the product.
Yes.
Looks like debris is laying on the west side there, is that right?
That would actually be a lack of debris because that, oh no, yeah, that is landing there. I'm upside down. Yeah, so there's some deposition going on there. Probably an ash fall. That's the right direction for that. Yes.
So I'm not really a geomorphologist, but watching this is interesting. So I'm curious, like, just from a qualitative perspective, how much of what you're doing here, like in terms of your like overall workflow, is like what someone who's in geomorphology would do, or is like the scale of process is so much different that like just like a rigor geomorphologist or something is
Right.
not doing this, or are you like basically doing geomorphology?
It's a lot the same.
Okay.
But the difference is like, riverine systems are different fundamentally than Lahar systems. The energies that are present, like the Roskin stream scale, breaks down completely when you try to apply it to Lahar paths. Like the sinuosity does not match at all. So this is I'm tiptoeing into unclaimed territory as far as this goes. Yes.
Yeah, so I'm kind of curious, what's the resolution of the PDF? Process, I'm guessing all of the DM that we just have the same resolution.
Yes, that's true. Okay, so the digital elevation models have been reduced to 10 centimeters per pixel. So since I wasn't able to have terrain tracking, I wasn't able to keep my my resolution consistent from the top of the digital elevation to the bottom, but all of them were below 10 centimeters per pixel when calculated at the ultra high level in Agisoft. Anything lower than ultra high, much to my chagrin, was about 11 centimeters per pixel, which makes the math a lot harder. So just process everything like to 11 to get everything to that point. But I was able to reduce it to 10 centimeters per pixel, and then the math worked all wonderfully.
What's the goal?
Oh, that is a data gap. Since I was flying around an active volcano, there was a lot of plume going on, and that got taken out in the post-processing. There's also data gaps that were necessary because eruptions were happening about 24 times an hour. It was a particularly active week for whatever reason, probably just because I was up there. So yeah, that's just a data gap. Yes.
So if you could do this over again, what would you do different?
I would not use MATLAB. Yeah, I would.
Soft, we'd use that.
Oh yeah, I would still use Agisoft. It's the best thing we've got going for. But I would switch to Cloud Compare, because then I would have been able to do this in 2 months instead of 2 years. Well, with what I know now, I would have been able to.
What about with data collection?
Data collection, I would have used a larger drone, one that doesn't have a black box around absolute altitude. The Air 2 doesn't give you anything but relative altitude from the takeoff point, which really messed with me when I was trying to reconcile 4 different survey zones, because all of them were 100 meters above the takeoff zone. So they're just stepped like this. So I had to reconcile all of them to get a true elevation, which was challenging to say the least. Oh yeah, absolutely terrain following. Like a 1000%. I would have used some other pre-programmed flight, which I've used since then for mapping different channels. I mapped Sinisa, one of the other Lahar channels, for a project between Jeff and Manuel Gomez for like Lahar outreach. And I was able to map that with terrain tracking and then also facade mapping. So I was able to get the walls of the channel as well. And I actually ended up collecting way too much data. I used 20% of the data that I collected for the actual finished product. I collected 10,000 plus photos, didn't use anywhere near that. But I had it this time, so that's what's important. Yeah.
Are there other processes that operate in these channels, like debris flows from the heavy rains, or are these channels like pretty much entirely modified by?
So the debris flows caused by rains are lahars. That's
Is
that.
that the difference between a secondary and a primary?
So the primary lahars are activated by eruptive activity. The secondary lahars are activated by the weather.
So what's the difference between a secondary lahar and a just a debris flow? Or is there really not a difference other than it's like on?
Mostly it's just because it's on a volcano, but the a debris flow and a lahar, they're very similar, but it fluctuates between hyperconcentrated flow and not hyperconcentrated. I don't remember what the other one is, but it's right on that border, and that's why it runs in pulses. It's got that watery front. That's just the definition. But it's very, very close. The big difference is that it's on a volcano.
So is there a sinuosity index for the Lahars? Or are you zeroing in on one?
So, yes, so well, it fluctuates throughout the season, but each section had its own sinuosity index that changed over time.
Is there something formulaic that somebody can use based on slope or moisture or terrain to as a predictive model?
Oh, as a predictive model. So it turns out slope didn't really have a whole lot to do with it in the end, because it was still down cutting through all of that pyroclastic material. Like oddly, I took the slope and there was really no correlation there. I didn't really see anything. As far as predictive models, yes, this probably could be fed into some machine learning thing, but do not know how to do that. Yes.
Your like vertical uncertainty, your
Right. So my vertical uncertainty, I was able to really neck that down. I got it within a pixel just through manual picking through and making sure that my overlap equaled 0 when it was supposed to equal 0. So I have very little vertical uncertainty that I can account for, just because I did it all manually. And it all equals 0. So I've got to Amilcar. These are great results and findings. Congrats. 2 questions. Do you think that your results can be applied without considering the type of lahar or flow? I mean, whether it's a debris flow, mud flow, or hyperconcentrated flow, could different parameters, deposition versus erosion, be expected? Yes. Yes, different different parameters and different parameters for different events could definitely change my outcome, but I think that all of this would still apply. But we can definitely apply this this strategy to other occurrences, other areas, anywhere there's really high volume or erosional processes going on. This could definitely be applied in those areas. And next for Brian, how do you see this type method / analysis pairing with other types of geophysical data? Again, as long as we've got some data differencing and erosion happening, we could probably apply most of this, possibly not the sinuosity index stuff, because it might not tell us anything. This is a special case because of that narrowing and then widening of the channel. It really pointed out that there was something happening there to point to. But if that's not happening, it wouldn't really give you anything useful apart from telling you that there was nothing happening there. All right, that's it for Zoom. Any other questions? Covered it all? Awesome. Yeah, so we'll be hopefully celebrating either congratulations or condolences at Mother Earth at 3:45. So I hope to see all of you there.
And we get to stay here.
Yep, this is our room. Okay, thanks everybody on Zoom.